All right. Hi, my name is Nicholas,
And my name is Ethan.
and today we will be presenting our Psych 203 demo day. For our introduction, we have why visual search matters. Visual search is a cognitive process we use to identify a specific object within a larger visual environment. This process relies on two important concepts that we have studied in class: sensation and perception. Sensation is the information that we receive, while perception is how our brain organizes and interprets that information. Our brain is constantly being exposed to an enormous amount of visual input. We must quickly filter all of this information to help us find what we are looking for. To understand how this process works, psychologists have developed several theories. Two of the most influential are feature integration theory and guided search theory. These theories explain how we search so effectively in some situations and so poorly in others. In this presentation, we'll explore both theories to understand how our brain performs this essential everyday task. Before we take a look at the theories, it is important to see how visual search is present in our everyday lives. For example, think about trying to find your car in a packed parking lot. Every car looks similar, and we are constantly trying to distinguish certain features of the car. This is a perfect example of visual search. Imagine being in a crowded place and you're trying to spot a friend. There are tons of people that look different, act different, wear different clothes. Meanwhile, your brain is working fast to match what you are seeing with your memory of that person. These are just a few examples, but they show that visual search is everywhere. It's something our brains are doing nonstop, often without us even thinking about it. Now that we've seen how common it is, the big question becomes, how does our brain actually do this? Let's start by looking at the first major theory, feature integration theory.
Okay, perfect. So feature integration theory, or FIT, was introduced by Anne Tresman in 1980 to explain how we combine basic visual features into complete objects. Take a look at the diagram on the right. At the bottom, we start with a stimulus pattern, a visual scene made up of different shapes and colors. These raw features are picked up by our brain in what's called the pre-attentive stage, shown in the middle as separate feature maps, one for color, one for orientation, motion, depth, and so on. This stage happens automatically and in parallel, meaning we process all of these features instantly without needing to focus. Then, using the attentional spotlight shown here, our brain moves into the focused attention stage, combining the separate features at one location of the master map to perceive a full object, like a green square or a red circle. But if attention doesn't bind the features correctly, we can make mistakes. These are called illusionary conjunctions, like thinking we saw a red X when the shape was actually a T. Now, to talk about evidence for fit, these ideas of illusionary conjunctions was tested in 1982 in a study by Tresman and Schmidt. If you look at the two images on this slide, you'll see how the experiment worked. Participants were briefly shown a grid of colored letters, like the ones in images A and B, then asked to recall what they saw. On the left, in the color singleton task, one letter stands out due to the color alone, like the blue T, and the participants were generally accurate. But on the right, in the conjunction task, the target features shares features with other items. So there are red T's, green X's, red X's mixed in. Under these conditions, participants often miscombined features, saying they saw a red X when only a green X or a red T were present. This visual evidence supports Fitt's claim: when attention is limited or distracted, feature binding breaks down and we confuse what we actually saw. Now to go into the actual applications of Fit, Fit helps explain why some searches are easy while others take effort. On the left side, we see a feature search. The red X stands out immediately among all the green X's, and this is fast and automatic because the color red is unique and pops out in the pre-attentive stage. But on the right side, we see a conjunction search. The target and a green O shares features with distractors like red O's and red X's, so we need focused attention to bind the shape and the correct shape and colors. That slows things down. In real life, this happens in a lot of different applications. In user interface design, we use color to make critical buttons or alerts to stand out in a feature search. Or for example, it helps explain why multitasking leads to more mistakes. Attention is spread too thin to bind features correctly.
So for some basics on guided search theory, Guided search theory was first introduced by Jeremy Wolfe in 1989 as a way to explain how we search for objects in complex or cluttered environments. Unlike feature integration theory, which focuses mostly on bottom-up processes, guided search theory talks about both bottom-up and top-down processes. Bottom-up processing refers to how certain features in our environment automatically grab our attention. This could be something like a really bright or unique color. Meanwhile, top-down processing is driven by what we're looking for, our expectations, past experiences, and what we want to find. Instead of randomly scanning everything, our brain uses a combination of these two processes to guide attention more efficiently. Our brain is narrowing down our environment based on both what stands out and what we are trying to see. This theory helps explain why we're better at searching for things in some situations, especially when we have a clear idea of what we're looking for. So, for evidence in guided search theory, the picture on the left is a great example of what bottom-up processing looks like. In this case, our brain instantly notices the red square among all of the green squares. This is because the red square visually pops out. It's unique in color, and there's nothing else competing with it. We don't really have to try and look for it in any effortful way. Our attention is pulled to it automatically. This is a classic example of bottom-up attention, where the stimulus itself drives our focus. If we look at the picture on the right, this shows what top-down processing looks like. We're trying to find a red circle, but it doesn't jump out nearly as quickly. This is because there are two types of distractors, red squares and green circles. This means the target shares features with other shapes, color with the red squares and shape with the green circles. As a result, your brain can't just rely on color or shape alone. Instead, it has to combine features and make a more deliberate search. This takes more time and attention. This contrast between the two images illustrates a core idea of guided search theory. Attention isn't random. Instead, it's guided by both bottom-up and top-down factors. When something stands out clearly, like the red square, attention is fast and effortless. But when the target is more complex or shares features with other items, like the red circle, we have to engage our brain more to find what we are looking for.
Okay, perfect. Now to do a side-by-side comparison of feature integration theory and guided search theory, we're going to look at the table. FIT proposes that attention is what binds visual features into objects, and it works well for explaining quick pop-out searches and why we sometimes make binding errors, but it doesn't account for our intentions. It treats attention as if it's purely driven by stimulus. That's where guided search theory adds value. It says attention is also guided by our goals and expectations. So if we're looking for a red apple, we're not just passively scanning, we're actively directing our attention towards red, round shapes based on what we want to find. Guided search is better at explaining real-world complex tasks, but it also means the process is computationally more complex. It requires more mental resources. So while FIT explains the how feature binding works, guided search explains the why behind what we choose to focus on. So this last slide sums up why FIT and guided search theory is important. In everyday life, FIT explains how we accurately identify objects in clustered environments, like picking out your keys on a messy desk. It explains visual errors like grabbing the wrong item when distracted. In terms of our class, FIT is essential for understanding how attention binds features into a single object, which directly connects to how we process and recognize what we see. In the bigger picture, these theories show how the brain transforms raw visual data into organized, actionable perception. FIT shows how we combine features, while guided search theory explains how our goals and context help prioritize what we see. Together, they help us understand not just what we see, but how and why we see it in the way that we do.